A pristine square of paper is a field of engineering potential. This flat, white surface contains enough geometric depth to build complex machines, provided you know where to place the first line. The practice of folding is woven into the haze of early Asian history. We see it preserved in traditions like the Senbazuru, where strings of 1,000 individual paper cranes represent a collective labor of patience and skill. This is a social and creative art that requires almost no overhead. You can begin right now with whatever scrap of paper is sitting on your desk. The craft scales instantly from simple play to complex art. A single sheet might become a 5-pointed star in a few minutes, or a multi-layered fish after hours of careful shaping. It is also an inherently collaborative process. If you've ever tried a tricky fold, you know that frustration is a normal hurdle, and leaning on a friend to solve a specific corner tuck is often how the best models are finished. Individual units can also be assembled into larger wholes. In modular origami, you fold identical units and lock them together to build three-dimensional geometric spheres and towers that hold their shape without a single drop of glue. These craft projects function because of a hidden mathematical language. When you look past the paper, you find a system of logic waiting to be decoded. A fold is a geometric line used to program physical space. Every crease pressed into the surface is an instruction for the paper. This network of lines is a crease pattern. It acts as the foundational blueprint, dictating how a flat sheet transforms into a three-dimensional object. By mapping these polygons, makers calculate volume and surface area. Analyzing the pattern also allows engineers to predict physical stability. The nodes where multiple lines intersect represent points of mechanical stress that determine if the final structure holds or collapses. Applying this mathematical lens turns the folding process into a deliberate act of mechanical design, where the user commands exactly how the material will behave. Modern pioneers like Robert J. Lang push this discipline into high-level mathematics, designing models of incredible complexity by treating paper folding as solvable equations. Designing a model like his 1-meter cactus requires mapping out the length and placement of every single spine through rigorous algebraic calculation. Because the math is so dense, designers use digital simulations to test folding patterns virtually. Tools like Origami Simulator let users experiment with structural stability and create new algorithms, nearly impossible to calculate manually. Digitizing the process confirms that the underlying geometry remains consistent, whether you fold physical paper or simulate the same movement in a virtual space. These principles are not limited to paper. Because the geometry of folding is a constant, it can be applied to massive structures made of metal, Kevlar, or high-efficiency solar panels. NASA is currently applying these exact mathematical principles to astrophysics through the development of the starshade. This is the prototype template for the starshade. The complex radial fold lines and the central aperture are designed to follow a specific, repeatable geometry. This configuration allows a massive instrument to collapse perfectly inward, fitting into the tight confines of a rocket for transport. Once in orbit, the structure executes its programmed movements to deploy. This is the final transition from a paper-based concept to advanced space engineering. The tools are now in your hands to move beyond following existing recipes and begin designing your own mathematical models. A single square of paper is a tool for engineering the future, and every crease you make is an exercise in the same logic that is expanding our reach into the stars.